dropped off, but we're going to talk about pH tonight, and that's the foundation of any good soil fertility program. And in any year, you really get a big return on your lime dollar. The last year or so, NP and K prices have gone through the roof. Lime is relatively about the same, maybe paying a little bit more for spreading and hauling feed to cover increased diesel cost, but for the most part, you're paying the same dollar for lime as you were $3 ago. So, or $3 ago, 3 years ago. So that's a big deal. What we're doing when we're liming, we're generally adjusting the pH up. You never lime to make your pH go down. So what we're doing is neutralizing acidity. And your soil pH is responsible for many things. The biggest thing is nutrient availability. And then you have root growth or root function. And then something we often don't think about would be herbicide activity. And I've got some examples of all three of those, or generally of two of those. We'll talk about the third in the upcoming slides. And you can actually hurt your crop yield, reduce yield without noticing, kind of a hidden hunger type deal. But well, we're just having all kinds of issues tonight. There's people in the waiting room, Philip. I'm going to try to get them going.
I got them taken care of.
Okay, now it's not letting me advance my slide. Oh my goodness. Is this on my end or your end?
Thinking it's on your end.
There we go. This is, I'm going to apologize up front. It might be a long night. We might just start talking and do a Q&A session for the next 45 minutes. But this missile diagram or bullet diagram kind of shows what our nutrient availability is at different pHs. The University of Kentucky says a pH of 6.4, 6.6, or 6.8, depending on which nutrient or which crop we're talking about. But let's just go with a general 6.5 for sake of argument, because that's pretty good. If you down there, the larger these bars are, the more available they are to plant uptake. And we're catching the fattest part of most of these bars around a 6.5 pH. When we drop down below 5.5, we see aluminum and iron become more available. They're fatter. Well, they're tying up our phosphorus. So when we reduce our pH, we reduce phosphorus availability. If we get too high, we start tying up phosphorus with calcium. The manganese is a essential nutrient, but too much of it is not a good thing. So when we get down to a more acid pH, manganese availability increases, plant uptake of manganese increases, and we decrease crop growth. Well, zinc is a micronutrient. It's needed in small amounts. And you can see, well, we have a very thin bar there, but it's a micronutrient. We don't need much of it. So we're in pretty good shape with our macronutrients, and then these micronutrients that we have. That mid-6 range is a good place to be. This was a slide that I got from Lloyd Murdoch about 11, 12 years ago when I started in this position. And I continue to use it because it really shows a neat relationship between soil pH and phosphorus availability. So what they did every year for a 16-year period, they added 80 pounds of P2O5. Now, the two bars, the blue and the pink, indicate that the pH was maintained at 6.2 and 6.6. And to be honest with you, I don't believe that. I believe that was their target pH, and they maintained a higher pH and a lower pH. But I don't think we're maintaining 6.2 and 6.6 for 16 years, but we did have a differential pH system there. What it shows is across all that, even though we're adding the same amount, that higher soil pH always has a greater soil test phosphorus availability. If you look on the left axis, let's just go to that 80, that first year, it was 15 versus 16 or 17, something like that. If we look at the end of the 16-year period, we had a soil test phosphorus of 60 with our lower pH, but it was 72, 73 with that higher pH. So just maintaining a proper pH is going to make phosphorus, for one thing, more available. This was one of those kind of aha moments. Again, I wasn't involved with this, but this was some long-term research done at Spindletop Farm there in Lexington, Kentucky, where 62 and 75 or 64 and 75 come together on the north end. And what they were doing was liming the plots. So I'm not sure 100% sure of the study, but I'm 100% sure of what I'm about to tell you next. They were liming the plots over many years to maintain a particular soil pH, but they didn't lime the 5 or 10 feet in between the plots. So the pH in the alleys are what we call the areas between the plots. The alleyway pH went way down. Guess what we have there? We have grass. Well, they treated the whole area with atrazine. Low pH reduces your atrazine activity. So there's an unattended consequence of, not managing your pH properly. Now, I worked in, this was my master's work back in the mid 90s. And what it has, it shows what happened after 14 years of continuous treatments. So the overall treatment structure we had a no-till and a tilled treatment system. And within those, we had no cover, which was just winter annual weeds, or we planted a vetch cover, a legume. And then within each of those systems, we had 4 different nitrogen rates. So this was for no-till cotton. Cotton doesn't require a huge amount of nitrogen. 90, I think 60 to 80 pounds was kind of the recommended rate when I was working in it. I've not kept up with nitrogen or cotton fertility, but 100 pounds is a lot of nitrogen, or at least was, to put down. It would have excessive growth, and then you would have issues with it wasn't setting a boll or wasn't setting a bloom, so you didn't have cotton. You had a lot of growth, all vine and no tater, more or less. So what this system shows, and this is without any lime, this is just 14 years of the continuous treatments. As we increase our nitrogen rates in any of those 4 systems, those 4 columns going down, our pH decreased. Just look at no-till, no cover: 6.2, 6.0, 5.5, 5.4. Look at the tilled and the vetch, the far right: 6, 5.5, 5.4, 5.1. So as we increase our nitrogen rate, our pH goes down. Nitrogen applications in row crop or in crop production is the #1 cause of a reduced pH for Kentucky agriculture, or actually agriculture in the Southeast. That's just part of the cost of doing business. So we add nitrogen from 0, 30, 60 to 90. Well, what if we go from the left to the right? So if we look in the no-till, no cover, it has a pH of 6.2 at 0 pounds of nitrogen, and it goes down to a pH of 5.8. Vetch is contributing nitrogen to the system. When that nitrogen nitrifies, it releases hydrogen. Hydrogen is what's going on with acidity. So if we look in any of those, do any of those comparisons from the no cover to the vetch always has a lower pH than the no cover. We just have some sort of contribution of nitrogen. What we did some rough math, and it was between 45 and 60 pounds of nitrogen was being contributed from this vetch cover crop. That nitrogen, whether it be ammoniacal from ammonium nitrate is what we used at the time, or ammonium from the vetch, we reduced pH with increasing nitrogen. So now we know why we've caused our acidity or our pH to go down. So what do we do to neutralize it? Really, there's one source that we use that works in row crop agriculture from a agronomic standpoint and economic standpoint, and that's calcitic or dolomitic limestone. So calcitic limestone is calcium carbonate. Dolomitic will have a certain percentage of manganese or magnesium with it. If you look on the far left of that top equation, CaCO3, calcium carbonate, the next one is plus 2H. That 2H is hydrogen. That's your acidity. It's consumed, forms carbonic acid, H2CO3, and that quickly dissociates to form H2O and carbon dioxide, CO2. H2O is our water. So if we go from the far left side, the 2H plus your acidity, to the far right, H2O, now we no longer have acidity. We converted that acidity into water. And the same concept works for the quick lime, hydrated lime. Those are not really used much in production ag. For one, they're expensive, they're hard to deal with, but they work. It's just not as economical and not as easy to handle as the calcitic lime. Pelletized lime, we'll talk a little bit about that later, but that's more or less just a bunch of the small particles of calcium carbonate or calcium magnesium carbonate compressed into a pellet and then spread. We also have some waste products. Actually, I was talking with the agent today about a paper mill waste product, and we were trying to determine what kind of acid neutralizing capacity it has. Philip and I talked earlier about a water product from a ham plant. It has some acid neutralizing or relative neutralizing capability. So if it can consume a hydrogen, it can reduce your pH or reduce your acidity and then increase your pH. So a lot of people think that calcium is what's actually doing the work as far as neutralizing acidity. So if you look at the gypsum and the calcium chloride reactions in the red, calcium sulfate, CaSO4, is gypsum. So if we look at that, we have that plus water, and then we have our acidity, our 2H plus. And then we have calcium, sulfate, water, and we still have our 2H plus. We were not able to consume that acidity, those hydrogens. And if anyone thinks about it, like, well, okay, why can't the SO4 match up with the 2H pluses? Well, that would be sulfuric acid. So if we did make it, it would quickly dissociate. So the sulfur is not going to consume the hydrogen. And if we look at our calcium chloride, and I'll speak more of this as we get deeper into the talk, CaCl2, we have the hydrogen, and when we react or when we apply the calcium chloride, we have calcium, we have chloride, and we still have our 2H plus. What's going on there? Kind of the same thing that's going on with the calcium sulfate. Calcium plus hydrogen is hydrochloric acid. So even if it could form association, it would quickly dissociate as a strong acid and not do anything. It would release the hydrogen back. So it's not the calcium, it's the oxides or the carbonates or the hydroxides that are consuming the hydrogen, and more or less you're taking that hydrogen out of solution and forming water. So we can't do that with gypsum or calcium chloride. If anyone tries to sell you gypsum or calcium chloride to neutralize soil acidity, walk away, tell them no thank you, give them my number or something, but don't spend money on those two products as a liming agent. Now, if you need sulfur, and that's a topic of discussion that I'm not going to get into tonight because Philip's got me talking about something else. But if you do, gypsum is probably the best source of sulfur if you know that you need it. But don't apply gypsum for soil pH management. This is kind of going down a little bit different road. So I felt like I'm speaking the truth up front to tell you some of the misconceptions that I commonly hear with lime. And if I'm hearing them, I'm sure you guys are hearing more. So there's several filters before I ever get to hear anything, but these are some of the more common ones. And I'm happy to have you tell me what you guys hear, or let April or Philip know and pass them along to me, because I always like to hear what's going on. And sidebar note, I know a lot of my information, or a lot of the questions I get sometimes come from Ag PhD. I'm not saying they're 100% wrong 100% of the time, but it's enough that when I hear something weird, I Google Ag PhD to see what's going on. But anyway, that's neither here nor there. So common misconceptions of lime. Pelletized limestone is better and faster reacting than ag lime. It's a quick fix. Well, that's not necessarily true. We'll talk about that. Liquid lime is much better than ag lime. And when I'm saying liquid lime, I truly mean a liquid or a suspended calcium carbonate source. That's not necessarily wrong or right. What is true is, on a per weight basis, liquid lime reacts as fast, or is as effective as changing pH as ag lime. The reaction time might be a little bit different, but this is calcium carbonate, not calcium chloride. And you'll see why I'm making this distinction in a minute. What is not true is, well, you can adjust the soil pH with a fraction of the amount of liquid or with that liquid product with a fraction amount as compared to the ag lime. That's not true. A pound of RNV is a pound of RNV. And then high magnesium lime causes compaction. That's not true either. So let's kind of go dispel some of these myths. Pelletized lime, here's some truths. It is granulated, it's finely granulated ag lime. So if you take a sample of ag lime, you have some real coarse stuff. It might be almost as big as dense gray gravel. And then you have stuff that's, like talcum powder. Well, these real fine ones, the more talcum powder like particles, are compressed, added some sort of binding agent, and formed into a pell. So they are usually high quality. Anytime you do any other step, any additional step, it costs money. Anything you do in any manufacturing process, every additional step has an additional cost associated with it. So it costs more than ag lime. I haven't priced it lately, but I did a couple years ago. And when ag lime was going for $15 to $20 a ton, the pelletized lime was going for about $300 a ton. So easily a tenfold difference. So it has a lot of fines and a higher CE, calcium carbonate equivalent. So then it's faster. Well, maybe not. That's a hard one to answer, but what I'm going to do is kind of walk you down an analogy that I think makes this makes it a little bit more clear. We just bought a new refrigerator, and it has one of these fancy ice cube dispensers. You can put it on cube and you get ice cubes like you'd reach in and grab. where you can put crush and they'll grind it and they'll spit it out. So if I get a pound of ice cubes or a pound of crushed ice, the same amount of ice, and I throw it out on the floor, I'm going to have smaller particles and bigger particles with the crushed, and then I'm going to have really big particles with the cubed. That cubed ice is not going to cover as much area. I'm going to have a lot more spaces I can put my finger down and not get it cold as compared to the crushed ice. And then let the sun hit it or just let it sit there for a few minutes. Well, we're going to get the floor wetter quicker with those crushed cubes versus the other. So, I mean, that's kind of the same concept as what we're doing with pelletized lime. Yes, it will break down, but lime doesn't move very far laterally in a soil profile. You know, you're not going to put a pellet down and then it move 4 inches or 3 inches one way or the other in a week or a month or maybe even a year. Whereas you're going to get a better distribution with the crushed ice. Same thing there. It is usually a higher quality product as far as your high CCE. So it might actually take a little bit less. That's not wrong. But, you know, if you have an RNV of 67 versus an RNV of 87, can you afford to pay $260 or $270 a ton more? No, the economics just don't work out. So that's my spiel about pelletized lime. I'm going to stop for a second or back up before I get into this next slide. I was working on my master's in the mid 90s, and one of the big things that was going around there, especially for tobacco growers, and I still hear it now as well, just mix 500 pounds of pelletized lime with your fertilizer every time you apply fertilizer, and you don't have to worry about pH. I'm not going to say that's wrong. I'm not going to say that's right. You are going to cover most of the acidity that you generate with some application. 500 pounds might be the right answer, might be more, might be less over time. Probably over time it's less, but what it's going to be more every time, regardless of, you know, what crop you're using, it's always going to be a more costly application. Again, $300 per ton versus $20 per ton. Let's just go up to $30 per ton. So, you know, that's $270 difference. You can do a whole lot of liming with $270. Now moving on to the calcium magnesium ratio of limestone. This is something that's goes back to base cation saturation ratio. That's part of the foundation of this argument, and it does have some deep roots in chemistry, except for we can't do this in the field. But they say too much magnesium causes compaction. Well, the truth is, yes, if you have high enough levels of magnesium, that particle or that magnesium is going to disperse the soil particles. That's true if you have too much. And then another truth is, if you have too much magnesium, these dispersed soils, so you have more or less muddy soil, muddy water going through the soil profile, carrying these very small clay particles. They're settling out in the pores, and over time, they fill up the pores, kind of like plaque does your heart or cholesterol does your veins. Well, if you infill or you fill up enough of these soil pores, you can reduce infiltration. That's all true, but we can't do it in the field. I said it's extremely unlikely. I think more accurately is impossible to do in a normal field setting. We can't find a calcium magnesium ratio greater than 1-to-1 in Kentucky. I think, yeah, okay. Here's here's an example of some quarries that we had. Oops. Well, I'll go to that in a second. Um, if we do happen to do that, 10 tons of lime, which is a huge rate, that's still just like 1% of the CEC when we're talking about a 2 million pound per acre fertilizer. So we don't have the magnitude, and I'll explain that a little bit more in a second. So I said we're not going to find a 1-to-1. We're not even going to get close to 1-to-1. If you look at the Roger Group quarry in Hopkinsville or in Princeton, the calcium percentage is 36, magnesium is 1.6. Nowhere close to more magnesium or even the same amount of magnesium. If you look below that, 38.3 to 1.1. And then I was looking for one to see if I could find one a little bit higher. So Bourbon County, 34.3% calcium, 3.1% magnesium. So, I mean, it was, that's not even 10-to-1. If those numbers were switched, if we had 34% magnesium and 3.1% calcium, and we applied 10 or 20 tons per acre per year, that could be an issue. But no one's going to do that. That just does not work agronomically. It doesn't work in a practical standpoint. So that's not something we need to get worried about. This was a slide that Frank Sikora made. It found a publication that shows difference between dispersed and flocculated soils. So if we look at 100% magnesium on the far left and 0% calcium, we see that dispersed soil. That's the muddy soil I was talking about, infilling the soil pores as water infiltrates. And if you go to the far right, that's pretty clear water. All the clays are flocculated at the bottom. Well, what's going on there? 99.3% of Kentucky soils have a calcium magnesium ratio greater than 75 to 25, so 3-to-1. And we had 1 part to 3 parts calcium and magnesium, twice as much calcium or magnesium as calcium with no effect. So we were way, way, way the other side of that ratio. Don't ever worry about compaction being caused by too high of magnesium in your lime. Now, if you did want to apply a lot of Epsom salt, you could, and you had a lot of money, if you had enough money to burn a wet mule, and you wanted to really mess up some stuff, you probably could apply enough Epsom salt to possibly do that. But you're going to cause a lot of other troubles or problems before you ever get to that calcium magnesium ratio that's causing compaction. So that's a non-issue. Just because we can do that in a lab doesn't mean it's real. So going back to some, real truths. How do we determine lime rate? Well, it starts with a good soil sample. We want to make sure that that soil sample represents the area of interest. And then, well, it depends on what crop it is, and we'll touch on that in a second, but pretty much everything we're going to deal with is 6.4, or tobacco is 6.6, or alfalfa, we have a pH of 6.8. If you're growing blueberries or something else, well, that's different, but we're talking about row crops and your forages, 6.4 to 6.8 our range. And then based on our water pH and our buffer pH, that's how we determine how much acidity we need, or how much lime we need to apply to neutralize that acidity. So just a little cartoon diagram, we have our active acidity, that's our water pH. That is what we measure with the pH probe, just in water, or UK uses a salt solution to try to overwhelm some of the seasonal fluctuations. But anyway, this is what we report, water acidity. And then we want to know what our reserve acidity. So if we neutralize that active acidity, those two beakers are connected. And once we neutralize the one on the left, the active acidity, that reserve acidity is going to fill up that pool until it's neutralized. But the buffer pH tells us how big that pool is. We start at a pH of 7.5, and then it drops down based on how much reserve acidity there's present. So it could either be small, or it could be the size of an Olympic swimming pool relative to that beaker. So the more that buffer pH drops down, the more reserve acidity we have, and the more lime we need to apply. And that's all calculated by the Socorro buffer test and our calcium chloride, or our 1-to-1 water. So what influences our rates? Well, told you about that, the amount of acidity, the amount of reserve acidity, and then the quality of the limestone that we use. As I mentioned earlier, most of the time we're shooting for a pH of 6.4, 6.6 for tobacco, just because historically it's had such a high nitrogen rate, just trying to stay on top of that nitrogen, knocking soil pH down, and then alfalfa a little bit higher. I'm going to be 100% honest with you. The University of Tennessee says we have a buffer, or our target pH of 6.5. 6.5 is a good number to shoot for. This is hand grenade science. It's not, brain surgery. If we get above 6.2 for most crops, we're going to be pretty good. Alfalfa 6.2 is going to be a little bit low, but if we're around 6.5, 6.6, we're not going to be hurting. But if I'm a 6.4 and I'm getting ready to establish a crop of alfalfa, I'm going to apply a little bit of lime, just to make sure I'm getting towards that higher end. We don't want to get above 7 because our micronutrient availability starts dropping down, but anywhere between 6.4 and actually probably 6.3 and 7, we're in pretty good shape for most crops. You want to be a little bit higher for the alfalfa mixes. So this is some stuff discussing surface applied lime, and my data shows a little bit here in a minute. Grove started, I believe, in 1983. He was your speaker the last 2 weeks. And in 88, he analyzed some work, and they found that, unless your pH drops below 4.5 or 5, your surface application of lime works pretty well. If you get below that, well, you might need to incorporate it. Just because you're pretty low, and lime, or the acid neutralization reaction, does not move through the profile very fast. But hopefully you don't get down to 4.5 or 5. You should be doing a little bit better than that. And then regardless of, let's say, okay, I did get down to 4.5, and you apply a pretty good slug of lime, even though your pH might not change that fast, you're getting rid of one of the worst things associated with a low soil pH, which is exchangeable aluminum. That really messes up the root growth. Root growth impedes the function of the roots to take up nutrients. And then if the roots aren't able to function properly, nutrient uptake doesn't happen as well. This is my data. I showed you what happened after 14 years of doing the same nitrogen cover crop tillage treatment, and this is what happens after we add lime. This is 3 years after lime. Same treatments that I showed you, we added the full rate. So this was a little bit different than most studies were set up. Every plot, we took the pH and measured it, and then applied the amount of lime for that plot. So we didn't just say we're going to put 2 tons of lime per acre. But what we see in the no-till with our lower pHs or our lower nitrogen rates, we got where we wanted to be. We were 6.6, 6.7, 6.4, 6.4. But when we started getting lower, we didn't quite make it. We were not bad with the no cover, but with the vetch, especially in the no-till, we just weren't able to do it. We weren't able to neutralize all that acidity produced. But with the tilled systems, we did pretty good. We mixed it through that 6-inch soil profile. So that was a good thing to do. And let me rephrase that. The tilled system in that situation neutralized acidity better. It wasn't necessarily a good thing to do. Would I get out of a good no-till system to make my lime react a little bit quicker? Probably not, but hopefully you're not in that situation where you have to make that decision. But regardless, this pH right here, the vetch with 90 pounds of nitrogen in the no-till, it was a pH, it had a 4.7 pH. Even though we didn't get up to our 5.3, it was still reacting, and it really didn't suffer much yield loss because we got rid of that exchangeable aluminum pretty quick. So the reaction or the relationship between fineness and reactivity comes down to surface area. If you take a 1-inch block of limestone and you just cleave it 4 ways, so instead of 1, now we have 8 1/4-inch blocks. If you put those together, they're 1 inch. We go from a surface area of 6 square inches to a surface area of 24 square inches. You keep doing that and keep doing that and keep doing that till you can pass 100 mesh screen, which is very fine. You would have approximately 60,000 square inches of surface area. That surface area comes back to that crushed ice. It's going to get into the soil. It's going to react faster. So 100 mesh screen, just to give you an idea how small this is, that means there's 100 holes per linear inch. So that's pretty fine. A relative neutralizing value, which is how you determine, the value of your lime, your effectiveness of your lime, depends on 3 numbers essentially. Your calcium carbonate equivalent, the CCE, how pure it is, and then the fineness. And the fineness is the percent passing through a 50 mesh screen, and then the percent passing a 10%, but not to 50. And then if it doesn't pass a 10 mesh screen, we give it R&V as 0 or a value of 0. So essentially, all the material passing through the 50 mesh screen, we say it's good, it's 100% effective. Half of that passing between, or that passes the 10 but not the 50, is effective, and none of it is. So calcium carbonate equivalent divided by 100 times that. That's how we calculate R&V. Just real quick, this comes in your soil test result. You can look it up in AGR1, but your water pH, your buffer pH, and then it gives you a amount of lime to hit a particular target pH. And then all of our lime rates or recommendations are now based on a 100% effective R&V, just like you would calculate fertilizer. So if I needed 100 pounds of K2O and I'm using potassium sulfate because I'm growing tobacco, that is 50% K2O. So to get 100 pounds of K2O, I add 200 pounds of the potassium sulfate, or I divide 100 by 50 or 0.5, and there's my 200. So the same thing you do here. I want 2 tons of ag lime or 100% effective ag lime. It's 67% effective. So I need to apply 3 tons of that lime to get the 2-ton application rate. And here's some good calculators. I'm sure everyone shows you these, but they're at the Regulatory Services homepage, gives you what you need, or tells you what you need based on what you have. The Economic Lime 2 compares up to 3 sources, and it includes hauling and spreading fees. So you might have one that's closer with a lower R&V compared to a quarry that's a little bit further with a higher R&V, and you can figure out which one's the better value. And then the one that I get questions on every year is the quarry results. If they don't get out soon enough, I get phone calls. These are sampled twice a year by the state and posted at the Regulatory Services page. Here's a copy or the screenshot of where you would see that. You can click on the year result that you're looking for all of 2022, and going back to what I already showed you. So we have the Rogers Group, Lafarge, and then Bourbon Limestone. If we look at the calcium carbonate equivalent for all three of those, they're pretty similar. Calcium carbonate equivalent is 95, 98, and 98 for the three. But if we look all the way over to the right, their effectiveness, the relative neutralizing value, they differ quite a bit, 62, 78, and 50. It's like, wait a second, that bourbon limestone, that's pure lime. It is. It's the best rock, but it doesn't have as many of the fines. It's not doesn't have the fineness associated with high quality lime, so it's not neutralizing the acidity as much. So you effectively need about a third more of it than you would from the Fredonia quarry. So this is something that you can give Philip credit for kind of starting. This was a Advanced Cal. They were marketing liquid calcium, but actually it was not, well, it was liquid calcium. They were started as liquid lime, but it was calcium chloride. So we initiated a study, started getting a lot of questions in 2021, and ended up with about 16 locations of field trials. We did it in small plot areas, 25 square foot of 5x5 area. And then we did a lab trial that used the same treatments. And what we had, our 4 treatments were nothing, or non-treated check. Used Advanced Cal at 5 gallons per acre. Generally, they said 2 to 4 gallons per acre is all you needed to neutralize acidity, but we went up on the high end. And then we used pelletized lime at 2 tons per acre, 2 tons of effective lime. So we adjusted it based on an R&V of 83. And then we used ag lime with the same rate at 77, R&V of 77. So the pelletized lime and the ag lime were going down at the same effective rate. Just a little bit more ag lime needed to be added. And here's a breakdown of the sites. We were pretty much all the way from the western end of the state to the eastern end of the state, down to the southern end of the state, and kind of got up north. There's a little pocket or two that we didn't hit, but feel like that was a pretty good distribution of sample sites. What we did before we ever put any treatments down, we tried to make sure we had a good soil site to use. So we were looking for soil pHs of less than 6. And then instead of trying to adjust every rate based on their pH, we just said we're going to put down 2 tons per acre. So we knew that we're going to under apply some and we're going to over apply some based on our recommendations, but we thought that was the best and most simplest approach. We then, once we decided this is where the plot's going, we collected initial soil pHs, applied all of our products, and then approximately 2 to 3 months later, we went in, took a biomass sample, took soil samples, and then a year after, after the initial application, we sampled again. Here's the data from the field site. So we have our check, liquid calcium, pelletized lime, and ag lime. Our initial soil pH was around 5.8, not too bad. If we look 3 months out, 2 to 3 months out, the check and the liquid calcium were pretty much the same as what they were at the beginning. But even 3 months out, we started to see a slight increase in the pH with the pelletized lime and ag lime. A year out, we had a little bit of an increase with the check and ag lime or liquid calcium, but that was more due to seasonal variation. I don't have time to go into that, but it bounces around from depending on soil moisture and things like that. But it's not really a 5.8 to a 5.9 is not going to get you too excited when you're going from a 5.8 to a 6.5. So we're not really doing anything there. And if you just look at the change variable, it really was within a unit plus or 1/10 of a unit plus or minus 3 or 12 months out, whereas the other ones increased as much as 7/10 of a unit. So we're actually neutralizing acidity with these products, the pelletized lime and ag lime, where we're not doing anything with the ones we wouldn't expect to do anything. Looking at our lab study, we had different incubation times, 1, 3, 6, and 12 months. Kind of the same results. We started with a pH of 5.2. Within 1 month, the pelletized lime and the ag lime shot up quite a bit. Now, these were in ideal conditions. You wouldn't expect this reaction to happen as quite quick in the field, but that's not too bad. 3 months, we still see a difference with the ag lime and pelletized lime, but checking the liquid calcium, still the same. All the way out to 12 months. We actually did something with the liming products, the pelletized lime and the ag lime, but the check and liquid calcium did not. So just be aware. Sometimes when it sounds too good, usually when it sounds too good to be true, it is. And please don't ever think that you can buy 3 gallons of a product and it be as effective if there is 3 tons of a product. It just doesn't happen. So we thought, well, we knew it wouldn't change pH. The research supported that. Well, maybe something else is going on. We looked at dry matter, crude protein, ADF, NDF, and TDN. No difference in any of those numbers. So not happening. And just a little math to show you why it didn't. I showed you the reaction before. So advanced calcium actually had a reported RNV of 0.45. The weight was 11.3 pounds per gallon. If we're looking at a 2 ton per acre rate, our RNV is 67%. It takes roughly 3 tons to get 2 tons of effective lime. If we use that advanced calcium product with that RNV, it's 444 tons per acre. Well, we're talking about a liquid, so how much is that? Roughly 80,000 gallons of water to make the same pH change as 3 tons of water or 3 tons of ag lime. That's equivalent to putting 2.9 inches of water per acre over a field. And it costs about $30 per gallon. So you can do some math real quick and say, ooh, that's pretty expensive. And the ironic thing is the pH right out of the jug is a pH of 4.5. So there's so many things wrong with this. Just please don't be sucked into their little spill. I'm going to skip over this. I can tell I'm getting a little bit late, so I'm going to try to move on. We have had some rain, so this isn't quite as applicable, but one of the things that we were seeing was soil sampling in dry conditions. First thing, you need to make sure you're hitting the proper soil depth. And then the two things, if you are, that would concern me with a real dry soil sample collection is soil pH. Do you use the salt pH or not? If you send it to UK, you do, then your pH is going to be pretty accurate. If you send it to some of the commercial labs, most of them still use a water pH. So you might be actually having a little bit higher pH or lower pH, I'm sorry, than what would happen with compared to the salt pH. And then soil test potassium. That will be a little bit lower if you think about potassium being tied up in corn stover. It will leach out when it rains, but if it's not raining, it's still contained in the residue. So if you're not getting rainfall, the potassium's still tied up in that residue. So you're going to have artificially lower soil test potassium levels than if you had a normal year. Just a real quick thing, look at the Zanesville silt lime slide at the bottom. So does soil test depth really influence soil test recommendations? Well, I was in a 5x5 square. I took samples from each of the four corners. I went to 1 inch, 4 inch, 6 inches, or 12 inches. And if we just look at the soil test P, that second column on the bottom table, at 1 inch, my soil test P is 90. Well, that's higher than we need to. That's higher than where we'd recommend an application. If we go to 4 inches now, it drops down to 45, then we would recommend 40 pounds of P2O5 per acre. Now, if we take it to 6 inches, now that's a 32 or a recommendation of 70 pounds of P2O5. And if we go all the way down to a 12-inch depth, now our soil test P is 15 and our application is going to be 100. So yes, soil test values or soil test depth does influence soil test values, which influences the recommendation. This is just something I did a few years ago. I never really finished up, but talking about the corn leaching from corn stover on the horizontal axis, the x-axis has inches of rainfall, and then on the y-axis we have pounds of K released per rainfall event. So we did this in the lab, just used a sprayer, added 1 inch per time in 1/4 inch increments. So we'd do an equivalent of a 1/4 inch, go to the next table, do a 1/4 inch, and then all the way around, and then start back over till we got 1 inch. Then come back a day or two later and do that again. So what we found, let's just look at the green bar. Our total amount contained in that stover or released from that stover was 40 pounds of K, not K2O, but K per acre. That first inch got half of it. And that's pretty much the same thing for the other 3 bars. So a little bit of rain goes a long way. 1 inch of rain is going to get, or at least it did here, about half of that potassium out of the stover. So if you're really dry, you're missing some of that. You get a few inches of rain, and we're getting that out of the stover into the soil where we can measure it. This is the same graph, just depicted a different way. That first inch or that second inch of rain. Just noticed that our at 1 inch of rainfall or 2 inches of rainfall, half of it's out. And I'm going to move on to wrapping it up so we can have a few questions. So just pH, it's a real big thing. It's a master variable. It influences nutrient availability, herbicide activity, root growth. It's one of the cheapest amendments we can add. However, don't apply it. It's not like nitrogen. You apply it and 3 days later your crop greens up. Give lime time. It takes about 3 to 4 years to fully react. So if you have an application this fall and you put down 2 tons of lime and you take a soil pH measurement next spring. Don't expect it to go from 5.5 to 6.5 in 4, 5, 6 months. You can spread lime anytime. Just be aware of your field conditions. Don't create compaction. And it's the cost per R&V, not the cost per ton. You can have some high quality lime that costs considerably more than a low quality lime, and it'll still be the better deal. Just use some of those calculators, pencil it out. Again, it's not calcium, rather it's the associated bases, the carbonates, the hydroxyls, the oxides that change soil pH. And I can't stress enough how good a soil test is of an investment. Saves money and time. Just make sure you're in the right sampling conditions. And kind of going back to that liquid calcium product, do you need it? Why do you need it? Does it pass the stink test? If it sounds too good to be true, then it probably is. Find some unbiased data somewhere. That's the beauty of extension. We don't get paid by anyone to sell a product. We get paid by you to support you. So if you have a question, ask your extension agent. If they don't know, they'll ask someone like me or someone that knows. There's a NCECRA 103 website. I put this out every year. There are so many products that have been tested, and they're located right here. It's a little bit clunky to use, but it works. And if the product you're looking at isn't there, just reason it through. Does it make sense? Can 1 gallon of a liquid lime do the same thing as a ton of ag lime? No, it can't. You can't make chemistry do that. If you want to try something, set up a proper field trial. Don't split a field in half and say, well, I applied half of this field and not on this field. And well, look how much better it looks. Well, maybe that field had a better natural fertility to start with, or something else is going on. Put in strips. And I guess the bottom line is, if it sounds too good to be true, then it probably is. So that's what I've got for tonight, and I'm happy to answer questions for a few minutes. I used up all my time, but we did have technical difficulties on the front end. So I'm going to say, let her rip.
Okay. We do have a couple of questions in the chat. If you have any other questions, feel free to put them in the chat. What is your opinion? Sorry, I lost it. We've got a power plant up here. What's your opinion about the sludge from the power plant? Would it have any liming value? Any ideas on that one?
Okay, so I'm going to say the sludge from a power plant is probably gypsum of some sort. And I know, and I'm trying to see if I can get to the chat, but so what gypsum is the stuff that runs through the power plant? They start with calcium carbonate, and then they force this smoke to go through there. The carbonate is consumed, and we end up with a sulfate product. There is some unreacted calcium carbonate in there, but from a practical standpoint, you're going to get very, 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 very little, if any, neutralizing capacity from that material. Now, if you are growing peanuts in North Carolina and need to help them peg, that's a good source of calcium. If you're deficient in sulfur and you know it and you can justify it, that's a good source of sulfate. But no, it's generally not going to be a good source. If it's thoroughly reacted as it should not be a good source of carbonate to neutralize your acidity. I see your lips moving, but I can't hear you speaking.
Sorry, I was talking to my guys that are in the office.
Okay.
If you all, this is going to wrap us up. I don't see any more questions. in the
I
chat
can't
box at the
believe
moment.
that.
If you think of anything, feel free to email me or April, and we will get those questions answered. We will meet next week at 6 o'clock to finish up the series to talk about spreading our fertilized dollars. So we got to get an economic talk in here. But other than that, I will see everybody next week, and we will get everything posted and emailed out to you. Thank you.
Thank you, guys. Appreciate it. Sorry for the technical difficulties up front.